let's talk about one of the most hostile environments you can possibly imagine: outer space. It's not just the vacuum, it's not just the radiation. It's the absolutely insane temperatures that turn every single mission into a constant battle for survival. So here's the fundamental question, right? Imagine one side of you is literally hotter than boiling water, while the other side is colder than liquid nitrogen. How in the world do you build a machine that can even operate, let alone do delicate science, in conditions like that? That's the puzzle we're going to unlock today. So before we can even get to the solutions, we have to really, truly appreciate the problem. For any spacecraft, the biggest challenge isn't some distant planet or a rogue asteroid. It's the very space it's traveling through. It is an actively hostile place for our technology. I mean, the sheer violence of these numbers is just staggering. The side of a satellite facing the sun can get up to 120 degrees Celsius. That's way above boiling. But then you look at the other side, just a few feet away, facing deep space, and it plummets to nearly absolute zero. We are talking about a temperature swing of hundreds and hundreds of degrees across one single object. See, here on Earth, air cools things down through convection, like a fan. But in the vacuum of space, there's no air, nothing. A spacecraft can't just shed its heat into the atmosphere. It's basically a giant thermos, trapping all the heat its own electronics are making inside while getting baked or frozen from the outside. So all these things just stack up to create an engineering nightmare. You can only get rid of heat by radiating it away. Your environment flips from a furnace to a deep freezer every single time you fly into a shadow. A super-sensitive science camera might need to be cryogenically cold, but the computer running it has to stay warm. And you have to solve all of this with hardware that's as light and small as possible, because every single kilogram costs a fortune to launch. Oh, and yeah, there are no repairs. You get one shot to get it right. The pressure is just immense. So who are the wizards that actually solved this impossible problem? Well, this brings us to the real heroes of our story today: the thermal engineers. Their entire job is to tame these cosmic extremes. And this definition from NASA, it just nails it. It sounds so simple, right? But as we've just seen, it's one of the most complex, most critical jobs in all of space exploration. They are literally the guardians of the machine's life support. And this just says it all. This is the seal for NASA's thermal engineering branch. Just look at the missions on there: Hubble, the James Webb Space Telescope. These iconic observatories and so many others simply could not function without the invisible work these teams do. They're the ones who make the science possible. So how do they do it? How do they pull it off? Well, they have this really specialized toolkit, a sort of survival kit designed specifically for the weird physics of space. Okay, so it all starts with multi-layer insulation, or MLI. You know that shiny gold or silver foil you see wrapped all over satellites? That's it. It's basically a super high-tech space blanket. Then you have radiators, which are kind of like the spacecraft's sweat glands, just radiating all that unwanted heat out into space. You've got tiny, strategically placed heaters that act like electric blankets to stop things from freezing solid. And then there are heat pipes. These are just ingenious devices that act like arteries, moving heat from where it's not wanted to where it can be dumped, all with zero moving parts. All right, let's try to build a simple instrument just to see why this gets so tricky so fast. First, you start with your optics. Mirrors or lenses. These have to be unbelievably stable. If they warp even a tiny, tiny bit because of temperature changes, your billion-dollar telescope is basically useless. Okay, so next you add the detectors, which are the eyes of the instrument. Now, to be sensitive enough to see these faint, distant galaxies, these things often have to be cryogenically cold. So now you have a component that needs to be near absolute zero sitting right next to electronics that are generating heat. This is the thermal engineer's ultimate balancing act. With the stakes this high and absolutely no chance for a do-over, the whole design and testing philosophy has to be completely bulletproof. You can't just design for an average day in orbit. No, you have to design for the worst day imaginable. I just love this quote because it sums up that mindset perfectly. Stacked worst-case conditions. That means they actually model a scenario where the spacecraft is at its absolute hottest, generating the most power, and its protective coatings have degraded over time, all at the same time. It's a philosophy of extreme, extreme preparedness. And the process itself is, as you might guess, incredibly methodical. First, every single component, right down to the last resistor, gets a strict temperature limit. Then, powerful computer models simulate the entire mission from start to finish. Only after all that do they actually build the hardware and then put it through hell in these massive thermal vacuum chambers that perfectly simulate the conditions of space, proving the design actually works before it ever dreams of leaving Earth. When we see these absolutely breathtaking images from space, we're really only seeing the final product. We don't see the silent, totally invisible engineering feat that kept the machine alive just to capture it. Let's just take Hubble. Every single one of its iconic images, from the pillars of creation to the deepest views of the cosmos we've ever had, is a direct result of successful thermal engineering. It's the system that works perfectly in the background, allowing all that incredible science to happen. So here's the big takeaway. Thermal control, it isn't just one of many systems on a spacecraft. It is the fundamental enabler. Without it, the electronics would cook, the optics would warp, the detectors would fail. Space exploration as we know it would just stop. So I'll leave you with this thought. The next time you see one of those stunning photos from the James Webb Telescope or a rover on Mars, just take a second to think about that invisible network of blankets and radiators and heaters that fought a constant, brutal battle against the extremes of space just to keep that camera alive. It's a hidden masterpiece of engineering.